a new paper here. It's not on Vixar yet, but I'll link it to the bottom when I get there. Using total axial angular momentum to determine the age of exoplanets, or why do planets spin at different energies? Now, I know for a fact energy is an abstraction. The school of Bill Gates taught me that. That's not the argument here. The argument is, why should the measured component of an object spinning be different in all the objects in the solar system? The nebular hypothesis has no explanation for that. Dogma, mainstream, however you want to word it, establishment, they have no explanation as to why Jupiter physically spins faster per revolution than the Earth, Mars, and all the others. Saturn also spins faster, and Neptune and Uranus spin slower. I'll go ahead and read this out, the abstract. Some ideas are presented to try and fit total axial angular momentum into the picture of gyrochronology. Gyrochronology broken up means spin, age, and study. So the age of objects can be determined by their spin. It's that simple. The total axial angular momentums are calculated for specific bodies made into a dimensionless number called Williams number. William is the name of my father's father. Just thought I'd use that name. Plus, it's a pretty common name. So, like the Dale Carnegie book, How to Win Friends and Influence People, the name you give somebody is the sweetest sound in the world to that person. So I thought maybe people would be more interested. A lot of Williams out there will see this and think, oh, they'll pay more attention to it. It's a pretty common name. So that's doubly why I gave it that name. The Williams number cutoff is arbitrarily set at 1 times 10 to the 3, so about 1,000. And I'll link this to the bottom, but I'll show you what I'm talking about here. You have Sun, Jupiter, Saturn, and Neptune on here. And of course, the angular momentum isn't perfectly calculated, but that's a dimensionless number. The Sun is right there. And now the age is up for grabs for the Sun. I'm not too sure where it sits at. Jupiter is more accurate, about 680 million years old. Saturn about 590. Neptune 1.12 billion years old. And as you can see here, that dimensionless number shrinks considerably as the star evolves. And I also did some other stars here as well. There's some various calculations there, some various numbers for you. Now, of course, all these are subject to change as well. The original Mercury age of 32.75 trillion years. That is up for revision. That's just to place it in the ballpark, because I just did the measurements against Earth to get that. I think it was 1/7,600 something times less axial angular momentum as the Earth. But then I put Mercury against Venus, because both of them have about the same inner core size. Now, the inner core size is what gives it away, because that's the minimum, the largest object, I think, that a star forms internally. And then that sets the baseline for how old or how long it took that star to form. So that sets the baseline for how much more of an atmosphere was actually there to create a core that size. I unfortunately didn't write that in this paper. I forgot. It's just the ideas are like this, and it's just I can't even keep up with it. I mean, it took me about 3 hours to get this one little paper down. It takes so much time. And when you have the ideas overflowing, you just have to get something down. So, of course, I'll come back to this and redo that. But anyways, when I set Mercury against Venus, it sits around 19.77 trillion. And then I put it against Mars as well. Mars and Mercury's inner core sizes are about the same. I think they're a little bit different. I'm not sure. But when I set that calculation up, when I compared it to against Mercury against Mars, it put Mercury's age as around 5.7 trillion. So between 5 and 32 trillion years old, Mercury is an old fart. Incredibly old. A fossil star, if you will. And of course, I have Venus in here, Mars, Earth, Uranus, and I don't know how far this is gonna go, but one of the main concepts, I already showed this graph in an earlier talk, is that it kind of goes like this. The graph, it sort of just goes boom, and of course this is log 10 scale for angular momentum. This is the dimensionless number. And this is log 10 scale for age as well. So it looks like, oh, well, the sun is only 10 times younger than Mercury. No. You got to remember, this is a log 10 scale. So this means it extends out enormously on the x-axis, and it extends out enormously on the y-axis. And the reason why I had to do log 10 for both is because we're dealing with objects that are so much different than each other. Planetary evolution is an enormously time-consuming process, and it involves an enormous amount of mass lost as the star evolves. It's basically the biggest physical theory that really exists besides galaxy formation. It doesn't hold, it's not up there with galaxy formation, and then stellar evolution right below it. As well, I did another graph here. You have that arbitrary cutoff of 1,000 Williams, and that is the young stars, and these are the old stars. And the reason why I did the arbitrary cutoff, you see Mars there is between 40 and 25 billion years old. The reason why I did an arbitrary cutoff is because when the star has its beginning axial angular momentum, the way that it loses its angular momentum, its spin, is by losing mass, because both mass and angular momentum are conserved quantities. When you remove the mass, you also remove the angular momentum. So that's where the majority of the spin is taken away when a star is young. But there reaches a point to when the star slows down its mass loss, and it can't lose mass in such a relative abundance as a younger star would, because the material is becoming more solid, more liquid. It's combining chemically. The chemicals are becoming heavier and heavier, so they sink, and it's really hard for them to exit, like diatomic hydrogen or diatomic oxygen. So that's the arbitrary cutoff. I have Earth sitting a little bit past that. Of course, this is up to change. And on the right side of this, the axial angular momentum loss is due to tidal interactions and impacts. So basically, you have something like Mars spinning, and the angular momentum of Mars, if it gets close to a host star, the host star's gravitational field will stir up fluid motion in its interior and cause it to kind of slow down because it won't be perfectly balanced. Think about the way to look at that would be, I know this is the perfect example, but like say you have a 2-liter bottle full of water and you fill it up halfway with water. When you try to roll it really fast down a hill or down the road, the water will come up and swish around on the inside of the bottle, and it will slow the bottle down. So the bottle will only go so fast because it's going down the hill and there's fluid in there. Think about the objects like Earth, which have a fluid mantles, and that fluid swishing around in there, which would cause it to slow down if it gets to spinning around a sun-like star too close. So I have those on the right-hand side of the diagram. Of course, they also lose mass via impacts, or lose angular momentum via impacts, which then excavate material from the surface. And of course, that's why I also had that previous paper about Mercury being about the same size as Earth and having its mantle ripped away over trillions of years. And the most important part about all of this is that we can finally understand why the Earth spins, why Jupiter spins, why Saturn spins, Neptune, Uranus, why they all spin. The nebula hypothesis doesn't have a physical mechanism to explain what should cause dust to clump together in the first place. Secondly, why should the dust even spin to begin with? Why should the dust spin? If it clumps together in the vacuum of outer space, what makes it spin? How do all the particles know where to travel? Gravitation is basically what do you call it? Omnidirectional. When you have a sphere and everything is going towards the center equally from all directions, there's no off-balance thing to cause the object to spin at all. Why is the Earth spinning? Well, it's because it's a highly evolved star. And its spin rate, it can be used to figure out how old it is. Spin rate, in addition to its mass and in addition to its radius, which is its total angular momentum. Of course, you have to do two sets of equations for that. But and then I have this graph right here. Now, it isn't a smooth transition, but it's more like an area. You have two solid lines on the bottom, one on the top, and you have potential areas where you can figure out how old the star is. I'll link this paper to the bottom when it comes up. I just submitted it to Vixra today. But anyways, hopefully that helps people understand one of the most basic things we could ever have thought of. All right, later, y'all.